Okay, AP Calculus AB, Unit 5, Day 6, warm-up and lesson. So go and try the warm-up. This is a function table. We started seeing these yesterday on the homework. These are very common on the AP test. It's a good way to test more isolated rules and just kind of give you generic functions. So go and show your work and find the answers. Pause the video right now and try these problems. See if you're getting the hang of them. Okay, the first thing I would do is I would find the derivative rule just in general. This is a good quotient rule. So that's going to be low d high minus high d low all over low squared. So then we're going to plug 3 in. And so it's going to be f of 3, g prime of 3, minus g of 3, f prime of 3, all over f of 3. These values in the table, f of 3 is 1, g prime of 3 is 2, g of 3 is 3, f prime of 3 is 0, over f of 3 is 1, squared, that goes away. The answer is 2. There you go. It's kind of work I'd like to see. All right. Next one's a good chain rule problem. So L prime equals the derivative of the outside first, leave the inside the same, times the derivative of what's inside. Chain rule. So then we're going to plug 4 in, where the x's are. And let's do that first. F of 4 is 0. And so g prime of 0 is 3. F prime of 4 is 4. And the answer is 12. There we go. Next one, let's go to product rule problem. K prime equals f of x times g prime of x plus g of x times f prime of x. So we're going to plug 1 in. And then we're going to look the values up. So f of 1 is 3. G prime of 1 is 0. G of 1 is 4. F prime of 1 is 2. So the answer is 8. There you go. Not too bad. All right. Now we're going to learn something new today. Like really new. So we've been learning a lot of derivative rules. And so far the way we've been doing derivatives has been done explicitly. And explicit means like very direct, straightforward. These problems, y is by itself. But now we're going to do implicit. So implicit is kind of like not direct, kind of backwards, kind of hidden. So we're going to have to do it on functions like this because there's no way you're going to get y by itself. Like, how are you going to do it? Now, sometimes we're going to do it on problems that we could get y by itself, but it would just be a lot of extra work. So it wouldn't make sense. Now, this is a problem that we did a couple of units ago when we were doing a bunch of review work, and I actually showed you this, but now we're going to be doing for real. So I'm going to revisit this problem where you were given this function and you were asked to find the slope of the tangent line to it. And we realized, oh, this is a circle. And so the way we did it back then was we were like, oh, the easiest way is to just draw a picture of it. And to be honest, it's probably still the easiest way. So on a test, on the AP test, I would do it the way we're going to do it here. Radius of 5. Okay, we would draw the picture, we would draw the circle. And then we'd put the point on there. We'd say, okay, well, 3, -4, that's like right here. And we want the slope of the tangent line. Well, the easy way is to take some knowledge from geometry and say, oh, well, these got to be perpendicular. Tangent line is always perpendicular. The radius has the point of tangency. So the slope of the radius, which is also the slope of the normal line, by the way, is down 4/3. It's definitely negative. Down 4/3. Just count down 4/3. So then the slope of the tangent line would be perpendicular to that, and it would be positive 3/4. So that's the way we kind of did it back then, because we were studying circles and graphs, and it made a lot of sense. Now, to do this one explicitly, you would have to solve for y first. And we can do it on this one. So you get, all right, x squared equals 25 minus x squared. Square root of both sides, plus or minus. And there is a plus or minus, because the plus is the top half of the circle and the minus is the bottom half of the circle. Now, in this problem, we'd say, oh, well, it's the bottom half of the circle because of the point we're interested in, right? So then you would take the derivative of this. You say, okay, well, that's a 1/2 power. So it means -1/2, 25 minus x squared to the -1/2. And then you have to do chain rule, which is why now we can do this, right? Now we can do chain rule. You could, clean it up if you want. The negatives cancel, the 2's cancel. It's x over the square root of 25 minus x squared. This is the derivative. And so then we could plug 3 into it. And it would be 3 over the square root of 16, and it would be 3/4. So yeah, that works. Now, implicit is we just take the derivative right away, just even without y being by itself. And this is kind of cool. This is probably easier than that. Definitely less messy, probably less work. We say, oh, well, the derivative of x squared is 2x. And then we're trying to take the derivative with respect to x, right? So we're taking derivative with respect to x. So it matters what you're saying. How are things changing with respect to what? To x. So the derivative of x squared is 2x. Derivative of y squared with respect to x, well, we don't, y is a function of x. We just found it on the last, right? I mean, if we wanted to, we could do this. We could replace it with something with x's. But instead, let's take the derivative with respect to y, 2y to the first power, and then follow it up with the derivative of y. Now, since we don't have it in terms of x, we'll just write that as dy dx equals derivative of 25 to 0. Now, I like to use dy dx for derivatives in implicit instead of y prime, because I actually had a y to the first power that looked like y prime. And y prime's in the middle of all this could get mistaken, because there's actual y in here. So I'm going to use dy dx. But that's how we do it, okay? Because y has an inner function. Y has an inner function, so we have to do chain rule, just like we've been doing, right? But we just don't know what it looks like, so we just say, well, derivative of y is dy dx. I mean, it is, right? So now we could solve for dy dx if we wanted, right? We could get dy dx by itself. Do a little algebra, 2y dy dx equals -2x. Divide both sides by 2y. And dy dx equals -x over y. And one of the things that usually happens is implicit differentiation. When you have y's in the middle of everything, we'll have y's in the answer. So that's kind of weird. Now, we could then go ahead and plug. Now, here's the weird thing. Like, well, okay, I'm going to plug x equals 3 in here, but what do I do with the y? We plug in the y value. So we're plugging in 3, negative 4. 3 in for the x, negative 4 in for the y, and we get 3/4. Now, if I were actually doing this problem in the future, I wouldn't go and try and get dy dx by itself. I would skip and just start plugging in the x and y values right away, because it's going to be easier to solve for dy dx if I just have a bunch of numbers anyways, right? So I would do this first and then get dy dx. And I think that's a bit easier. And on this problem, it might not seem that big a deal, but on other ones, it'll probably make a big difference. So I would skip getting dy dx by itself if I was trying to get an actual value. Now, if the answer was the derivative itself, a formula, then yeah, you got to do that. So anyways, so this is implicit differentiation. We're going to be practicing that today. So let's do a couple more examples on the back to get the hang of this. And it's a lot better than trying to do it explicit when you're not given an equation that's explicit. So this problem here, find the slope of the normal line. Well, you got to find the slope of the tangent line and then find the perpendicular slope. Now, trying to get y by itself here, it's not going to happen, right? So, I mean, we did that last problem implicit and explicit because we could, but can't get y by itself, or it's really hard to do, right? Or maybe it's not that hard, but you just don't want to do it. Okay. And we can't draw a graph of it. So we can't do the geometric approach, right? So we have to do implicitly. All right, that's our best option. So what we're doing now, I'm not going to write this every time, but this time I'll do it. This is essentially what we're doing. We're taking the derivative with respect to x, and what you have to do is you have to do it of each term on each side. This is what we usually do. We take the derivative of each term with respect to x. Now, usually the y is by itself, so that's where we get the dy dx from. Now, when I take derivative of this, there's a product rule. So I got to do that. I got to do, okay, well, x squared times derivative of y. Well, derivative of y it's 1 with respect to y, but with respect to x, you get a dy dx. Plus y times derivative of x squared is 2x. So that's just that first one. So every time you see y doesn't mean you're going to get a dy dx, only if you're trying to take derivative of it. So product rule says this times derivative of that, which we did, and then this, just whatever it is, times derivative of that. We have another product rule here. So I like to put these parentheses around here just to kind of like make sure I don't forget to finish something. X times derivative of y cubed would be 3y squared, but that's only with respect to y. So that's like the outer rule, and you got to follow it up by the derivative of what's inside, dy dx, plus y cubed times derivative of x is 1 equals derivative of 64 is 0. So you've done the derivative now, okay? Right? You've done the derivative. In fact, we're getting dy dx's in multiple places, which is actually not uncommon. So this is pretty gross. We're going to have to try and we're going to go ahead and try and get dy dx by itself. Now, in the future, I wouldn't, because we're actually going to evaluate it at a certain point. So I'm going to show you the way in a second. Let's say if we were trying to get dy dx by itself, well, when you just solve equations for variables and they're showing up in multiple places, usually we combine them together. But these coefficients can't be combined together. So what we do is we factor the dy dx out, and you get x squared plus 3xy squared. And then I would move the other stuff to the other side. And this is just general solving strategies, right? The thing you want to get it all together, combine like terms, move the other stuff to the other side. So we're going to have a negative 2xy minus y cubed if we move those to the other side. And then we're going to divide both sides by what's multiplying dy dx. That's going to be negative 2xy minus y cubed over x squared plus 3xy squared. So that's dy dx, if you were being asked to find it, okay? Now, since we're being asked to use it, I mean, we could go ahead and then plug in 4, 2 into this. It's going to be negative 2 times 4 times 2 minus 2 cubed over 4 squared plus 3 times 4 times 2 squared is going to be negative 16 minus 8 over 16 plus 48 equals negative 24 over 64 equals negative 3 over 8 is the slope of the tangent line, right? And so the slope of the normal line is going to be positive 8/3. Okay? Now, if this was my end goal and I didn't really care about finding dy dx specifically as like an answer, I would have jumped from here. I would have skipped all this and I would plug 4, 2 in right away before trying to get dy dx by itself, because I think that was kind of a mess trying to solve for dy dx with all these letters everywhere. That makes it a lot harder. But if we plug in the numbers right away, 4 squared dy dx plus y is 2 times x is 4 plus x is 4, y is 2 dy dx plus y is 2 equals 0. Just plug all the numbers in. Don't try and get dy dx by itself first. And then, figure out what the numbers are. 16 dy dx plus, that's another 16 plus 4 times 3 is 12, 48 dy dx plus 8. And now, if I want to solve for dy dx, it's easy to add these together because they actually do have coefficients that can be combined together. And then the 24 I can move to the other side and then divide by 64. And then I get dy dx equals negative 3/8. I think that's a lot easier than what I did up here. I'm not saying it's even necessarily that much less work. It's just easier work. It's just a bunch of numbers. So if you have that option, I would do that. Now, if you're asked to find dy dx as an equation, well, then you're going to have to find it as an equation. Okay. Why don't you guys try the next one? So just see, if you wait till try the first one on your own on the homework, you might realize you don't know what you're doing, run into issues. So you should try it now. So try this problem right here, and actually try and get dy dx by itself, because that is the one thing we're being asked for here. Okay, we're not going to plug in a pair of numbers, so we can't use that little technique I was just describing. So pause the video, try this problem. Okay, assuming you tried it, we're taking derivative with respect to x. Derivative of x is 1. The derivative of y squared, well, the outer derivative is the squared. You get 2 times y to the first, and then you got to follow it up with the derivative of what's inside with respect to x, which we don't know what y is in terms of x. By the way, getting y by itself would be horrible. Plus, derivative sign is cosine. Leave what's inside the same. Chain rule says, okay, we'll take derivative of what's inside, which will give you 3y squared. Chain rule again says derivative of y is dy dx. Okay, so now you've done the derivative. But now we got to do the algebra to get dy dx by itself. So we could factor dy dx, and there would be a 2y plus 3y squared cosine y cubed, right? And then we're almost there. Dy dx equals 1 over 2y plus 3y squared cosine y cubed. Not bad. Not bad. Okay, you guys, try the next one. Let's see. Let's try it. Hopefully you tried the last one. Maybe you had a little trouble. Now you're like, oh, okay, I get it. Okay, do it. Prove it to you. Prove it to yourself. Try it out. And we're going to go ahead and solve for dy dx. Not plugging numbers in on this one. So you want to get the dy dx by itself. So pause the video, try this problem, and then unpause. Okay, I'm assuming you tried it. Derivative sign is cosine x. So nothing extra needed because it's just x. Derivative y is 1, but we need to follow it up, dy dx. Derivative cosine is negative sine, leave the inside the same. Ooh, but now we got to do chain rule times derivative of what's inside, and that's a product, so you better put parentheses around the next part because you get multiple terms. It's not going to make sense if you don't put the parentheses, if you somehow even pull out the right answer, which you probably won't. I'm telling you, this is going to be a big issue in the next test. Guaranteed. X times derivative of y be 2y dy dx plus y squared times derivative of x is 1. And all this has to get distribute to both of those terms. And if you don't put parentheses around it, you're probably not going to do that. And even if you do, then that's even kind of more weird. Okay, so now we want to get dy dx by itself. So I think it would be helpful to go ahead and get rid of those parentheses first. So we're going to say, all right, minus 2xy sine xy squared dy dx minus y squared sine xy squared. So I'm trying to write these in kind of the more nice format that I usually expect. Now here's your dy dx's. This guy's going to go to the other side or vice versa. I mean, it's up to you. I mean, cosine x plus y squared sine xy squared. And then we're gonna factor out the dy dx out of these two terms to get them together. 1 minus 2xy sine xy squared. Right? And then we're almost there. Dy dx equals cosine x plus y squared sine xy squared divided by 1 minus 2xy sine xy squared. Can we like cancel these sine xy squareds? Yeah. No, because you're canceling just individual terms in a fraction. You can't do that. It's got to be something that you divide out of everything on top and everything on the bottom. This is it. This is the best answer. Okay. So, this is your assignment. I'm going to go ahead and let you skip 29 and 31. Okay. So there's only 7 problems. They're all odds. Check them in the back of your book. Check them as you go. Make sure you're getting them right. If you're not getting them right, try and figure out what you're doing wrong before you get really good at doing the whole assignment wrong and have to fix them all later. So that's it. Try them out. Implicit differentiation.